Awesome. Okay, thank you. So first, I would like to start by saying thanks, Camilla, James, and Keelan, by organizing and have this awesome conference. That's, I mean, lots of topics to cover during the day, but it was really nice to be part of this. So today, I'll be talking about developing strategies for continual detection with the AMM detection toolbox. My name is Angelo Menezes. I'm a PhD candidate at the University of São Paulo here in Brazil. Today, I'm going to be, quick with my considerations about this topic, because mostly it's some of the discussions that are going to be bringing today are kind of opinionated, but I will just describe how the AMM detection toolbox works and why if you want to develop something for continual detection, you should choose it as your main library. So first, on a small agenda, I'm going to give a context about continual detection, some current alternatives, the AMM detection for continual detection, how you can use it, like how the library internals actually work in a highly level comparison, in just a quick tutorial, and conclusion of some final considerations about standardization. So what is continual detection? So continual detection actually falls behind the umbrella of incremental detection, which was the most common word used for this in the 2020s and 2010 decades. So pretty much now, if you try to search about this topic, you're going to find things like class incremental object detection, domain incremental object detection, and data incremental. So pretty much we have on the top continual and incremental object detection, and just below it we have class incremental, domain incremental, and basically data incremental. So in those scenarios, what we want is having a model that can deal with data that comes mostly as a string. So supposing that we have a class incremental benchmark, ideally is that in the next task that we're going to be learning, this next task probably will have classes that were not seen previously, and they might have appeared as the background, for example. And in domain incremental scenarios, we would have a domain shift on the classes. So pretty much a person that appears always on a grass background, with a grass background, probably now the person is going to be appearing in a indoor background or something like that. And the data incremental would be a scenario where we have class and domain incremental all together in the same benchmark. So because of that, we have like COD, YOD, CYOD, and DYOD. Like we have several terminations, but ideally they all talk about mostly the same thing, which is like having a detector being able to adapt consistently with the arrival of new data. So why do we need that? Because most of the times we need generalization and efficiency. So if we have all the computational time in the world, we could always gather all the data and train from scratch. But most of the times, like this might not be able to happen. And in this way, we might train the detector to detect parts of a tower, transmission tower, for example. But then we need to generalize to new towers or new objects that didn't appear or appeared but were not labeled. So basically, the continual detection literature needs to deal with all these situations. And how we have done that? Okay. Basically, most of the researchers have used the base of continual learning for classification to propose strategies for continual detection. So in this small list here, you can see that covers pretty much all the works that were proposed up to the end of 2021. You can see that most of them were based on knowledge distillation, and just a few of them actually take advantage of of some detection properties. So, for example, the use of fake labeling, the use of more specific scenarios for replay, and yeah, well, pretty much what people have done so far is like taking continual learning for classification and trying to adapt for detection. But okay, let's suppose you are new on the topic. You just trained your detector with YOLO on your new data set, and you want a fresh start. You want to know, okay, what if new data arrives? How do I do it? What should I do it? So let's talk GitHub. And from this point on, I'm going to disclaimer that these are some opinionated considerations about it, because I felt when I was trying to deal with this as an engineer before, and now as a PhD candidate, and I've talked to some students that I wanted to bring to this continual learning for object detection field, and they all, I mean, like, we actually we reached common ground in some of these opinions. So I'm gonna talk about our current alternatives for continual detection. So the first paper that came with continual detection was in 2017 by Shmelkov, which is mostly called, the strategy is most that he proposed is mostly called ELOD. And we have his implementation on GitHub, but it is using TensorFlow 1.5, and it's, I mean, like, it's good for having as a reference, but most of the researchers actually could not reproduce the same results that he got there. The same happened to faster ELOD, which was proposed in 2020, and it was based on the Mask RCNN benchmark that was written by Facebook at that time. But as the project was not maintained, pretty much the results that we get are not comparable to the ones they got in the paper, and it's really difficult to actually move forward with implementations. From 2021 on, most of the researchers have focused in using the Tectrum 2 for that, for proposing solutions, continual learning solutions for object detection. And one point that is nice to highlight is the work of Joseph, that actually implemented incremental detection with meta learning. And based on that, he actually wrote several papers following and using his the structure of his own repo, and it's really well structured, but still the detection 2 has a really abstract structure, so it's kind of difficult to understand what are the changes that are needed to make it work in an incremental way. So as you make something really abstract to, you know, incorporate all the possible scenarios, sometimes it becomes really difficult to do specific work. So in this way, by talking to some students that actually try to do incremental learning with the Tectrum 2, they said that, okay, in the scale from 1 to 5, 3 from easiness to learn, the code is not maintainable, like, because it is maintainable if you keep all the versions and all the things inside the box. But I mean, if you found a bug, probably this bug, you are on your own to actually solve the bug, fix the bug. And reusable code, the nice thing is because the Tectrum 2 actually has some nice implementations for object detection. So you can reuse strategies for example, visual transformers and newest architectures on this with this framework. Great for setting up multi-GPU instances. So this is actually good because it was thought to be a framework for mainly object detection. It has implemented several object detection baselines, but it is hard to identify the changes needed for incremental learning and not actively maintained. So Avalanche is a great library for continual learning for classification, and it has actually been used in some competitions for object detection, for continual object detection as well. Some of them are listed here, and talking to some students who were exposed to Avalanche, the easiness to learn, I mean, from a perspective of people who are versed in object detection, they said that Avalanche was easy to learn somehow, but it had some abstractions and it was difficult. The documentation was clear, but it was difficult to do some specific work that is some work that is specific to object detection. So changing specific losses, creating a specific region of interest heads. So they mentioned that it's complicated because you mostly need to deal and propose and write the code to work outside of Avalanche, and then you need to bring everything up inside Avalanche. So it kind of, the code is pretty maintainable. It's great because all the issues are being tracked. But on the context of for object detection, there are like really few implementations that actually are using Avalanche for continual detection. So this makes it, you know, a rough start. So it's great for standardization of continual learning research in general, but might be cumbersome for people who are starting new in the field. So with that in mind, I bring to the table detection for continual object detection. So detection is a toolbox that is really famous inside the prediction, inside the field of practitioners for object detection and computer vision in general. So it's maintained by OpenMLab, that is maintained by several Chinese institutions. So they've got options pretty much for everything that you can imagine about for computer visions, which is pretty great, because if you learn the OpenMLab way of doing things, you can pretty much transpose this knowledge to every part of the computer vision realm. So you can apply this for action recognition, tracking, and such. The nice thing about detection is because it comes with lots of implementations for the oldest to the newest architecture. So you've got like all the changes for the YOLO series. You've got the Foster RCNN traditional method. You've got the vision transformers and their variations. So this is pretty good. And this is actually nice to start, because most of the times when you are getting up doing partitioning with incremental learning, you do want to test all the things that are possible to work. So pretty much every time they find that there is a new technique that performs well, they go there and they implement it, and it's pretty great. The easiness to learn, it's still, talking to my students, they said that it's a generic code base, so it might be a little be difficult to get on track, but the code is pretty maintainable. So people actually pay attention a lot to the issues that are over there. But as there are like lots of people using it, sometimes some bugs can happen and can be found, and not everyone will be able to actually help. And the code is pretty reusable, because they implemented lots of losses, lots of dense heads and backbones and necks that are specific for detection. So it's the abstraction there is specific for detection, which is kind of great. It's great for setting up multi-GPU settings, actively maintained, easy to adapt to incremental learning, but sometimes it can be a little rough for beginners. But if one needs to choose the path, it needs to test several options, and this one might be a nice option. So I'm going to talk here like really quick about some of the internals of the library. So the nice thing is, because everything is highly customizable, so they got data sets that you can use out of the box, and you can pretty much inherit the features and the methods, everything, the attributes that are present on the main data sets, and then you can create the incremental versions for that. So you can do this for VOC, for Pascal VOC, for Coco, for Elvis. So this is great. All the models are split into some customizable structures. So you have the backbones that can be easily changed. You can have the neck that process all the features that come from the backbones, and based on the neck, you can either have a dense head for single stage detectors, or you can even have a region of interest head to propose some to have some object proposals that can be classified in the dense head. So they've got this abstraction that works pretty nice out of the box for object detection. And this is pretty great. And one point that is actually quite nice is because, for example, for implementing a new loss, you just, they've got this Python registry pattern that you can just declare it, and then you use it in a really nice way. I believe most of the new architectures are following this structure, but the way they place it for object detection might be actually really good. So just going fast, Camilla probably appeared, so it might be a way to, okay. So talking about the really differential part is because, for example, for working with continual learning, we need hooks, because we need separate things to be able to happen before either setting. So we might need to change the loss, we might need to change how the classifier, how the neurons are going to react every direction, every epoch. So we've got hooks for every part of the training pipeline. So this is quite good. This is actually pretty similar to the Avalanche pipeline. Probably they took inspiration from it. So this is pretty great. They have customizable data set pipelines. So as I mentioned, you can just inherit from the VOC data set and create incremental settings out of this. And for training, you have the training script, you have a training API. You just use your configuration file, and you can, specify, okay, I want this train distributed. Yeah, I want for certain epochs and everything. So this is actually pretty good and really nice for standardization in the field of continual detection. So the main takeaways today are just that my detection can be a nice starting point for doing research in COD. Standardization is key. It's key for a well-developed research field. If you see the gains that the gains that actually Avalanche brought to the continual learning field are tremendous, and most of this is because of the standardization. People can actually use the code there to build and to do things more advanced in the future. So this is quite good. And continual detection improves every time continual learning and object detection improves as well. So that's a nice segue. Just a nice comment is that the implementations of some traditional code baselines using detection will be released in the next few weeks in my GitHub. There is a specific directory there. So I have implemented some of them. I'll be releasing the next few weeks. So that's it. Thank you.
Well, wonderful. Thank you so much for that great presentation, and not only of this particular library, but in general of so many continual learning open source libraries. So we have one question. Yes. Oh, sorry. I think this is an answer from Adri to the previous question. Sorry for the confusion. So maybe one question from myself. If somebody would like to get involved in the development of detection, what is there that possibility or?
Okay, so the nice thing about detection is because they are really open with their issues. So if you go there and talk to them and you found something that you think you can help them, you can just talk to them and say, oh, this is I can actually solve this. So you can go there with the issues and do do the work directly on their library. But if you want to do, for example, something else and say, okay, I want to do continual detection and I want to make a baseline based on something that they have already implemented, you can just point them like in their issues and say, oh, I've done this. And so probably someone is going to take a look and say, oh, nice. So they're going to link on the main repo and probably help you as well. Like say, oh, you did that. So you might optimize this in a better way. So people there are really nice.
Okay, wonderful. That's good to know. There's one more question here. Are there COD methods that start with strong pre-trained models? So is there support for strong pre-trained models within the architecture that we can just continue training?
The nice thing about the detection, and actually all the libraries that are developed by OpenM Lab is because they all are interconnected. So they've got a specific library called pre-train, where they pre-train models specific for some tasks. So they can use, for example, they can have self-supervised strategies for training a visual transformer as the backbone. And you can take that backbone directly from their repo and just link it with just a few lines of code. And okay, I'm going to use this one for detection and see if it works best. So that's pretty nice. They have got like a full list of different backbones specific to detection and to other fields as well that can be tested.
Okay.